Hi there and welcome to another Framework GCSE Maths video where we look at a circle theorem question from a higher tier Edexcel maths paper. Most students find circle theorems difficult to solve, which is completely understandable because this type of maths also requires having a certain level of spatial and visual perception. And unfortunately, most of the questions you come across are not drawn out in the nice simple ways that textbooks describe circle theorems. This video describes a framework that uses an elimination process to work out which circle theorems you could use to help answer the question. The video is therefore quite long because it describes the 8 circle theorems in detail, so feel free to skip parts of the video that's not relevant for you. In this video, in this particular question, we're asked to work out the size of the angle ADC. And at first glance, we could assume that a possible clue is that the angle sits on a straight line CDE, but the question gives us very little information. Before working out the problem, I'll use the next few minutes to explain the 8 circle theorems and the terminology. In this diagram here, there are a number of lines and spaces in the circle that have specific definitions, and it's helpful to understand what these definitions actually mean. So let's start off looking at the bottom of the circle with what looks like a slice of pizza, where we have 2 lines from the center of the circle touching the sides of the circumference of the circle. These lines represent the radius or the radii, a single one, and the enclosed space of the 2 radii is referred to as the sector. The circumference that is enclosed by the 2 radii is referred to as the arc, or a section of the circumference. Moving anti-clockwise up around the circle, we have 2 lines, AB and AC, that do not go through the center of the circle and are referred to as chords. If the line was to pass through the center of the circle and touch the opposite side of the circle, then that line would be the diameter, denoted by the dashed dotted line here. As we travel round the circle in an anti-clockwise direction, the space trapped between the arc, remember that's the section of the circumference, and the chord AB is referred to as the segment. And carrying on around the circle here, we have the angle that is created between the 2 chords AB and AC. This angle is subtended, or the subtended angle. The last point on our circle is a tangent, which is the green line, which is a straight line that touches a single point on the outside of the circle. Now, it's helpful to understand the terminology described in the circle, but the most important thing to recognize when circle theorems is listed out in step 4. And you need to ask yourself, do the lines go through the center of the circle? Do the lines touch the sides of the circle? Are there any tangents? Do you recognize any triangles? Can you draw the lines in different colors that would help you identify those kind of shapes more easily? And the last point is more challenging, is mentally think about repositioning these lines that already sit on the sides of the circle to generate a slightly different shape. Hopefully that will give you an idea of the type of circle theorem you can actually use. The framework we use to solve circle theorems is based on the process of elimination, where there are 4 separate questions you need to ask yourself and consider whether this is a possible theorem that you could use. Each step is covered in more detail in the next 4 slides. Step 1 is to eliminate whether you can use the cyclic quadrilateral theorem. Here you have to ask yourself, does the shape inside the circle have 4 sides, i.e. a quadrilateral, with each vertice actually touching the circumference of the circle? Also note that none of the lines pass through the center of the circle. And in this theorem, the opposite angles of the quadrilateral add up to 180 degrees. So in our example, angles D plus B add up to 180 degrees, and angles A plus C also add up to 180 degrees. Step 2 is designed to eliminate whether there are any tangents involved in the question. If there are, you need to consider 3 possible tangent-related theorems. In theorem 1, the tangent of a circle, the angle between a tangent, or the green line, and a line from the center of the circle to the circumference, or the radius, is 90 degrees at where they cross. In the second tangent of a circle theorem, you have 2 connecting tangents, 2 green lines here. Where the tangents meet at the point C, the lengths of the two tangents are equal. The third theorem, the alternative segment theorem, is more complicated and covered in more detail in the next slide. The third tangent-related theorem is called the alternative segment theorem and is perhaps one of the most confusing theorems, both because of the language that's used and also recognizing the angles the theorem refers to. So let's look at this one in a little bit more detail. The first thing to recognize is that you effectively have a triangle ABC, and that it has one vertice that is touching the green line or the tangent. Notice also that all 3 points touch the sides of the circle. Now there are 3 ways of thinking about the theorem, and you can choose the version that works for you. The first way, and perhaps probably the most mathsy way, is using the actual wording for the alternative segment theorem. The alternative segment theorem says that the angle between the tangent, the green line, and the chord, the red line, is equal to the angle in the alternative segment. If you remember from our earlier definition of a segment, it's the area between the arc and the chord, which is here, the red line. In this case, we have 2 segments, sometimes called a major segment and a minor segment, because the circle is split by the red chord. And the alternative means the opposite side. So the angle created in the minor segment here, between the red line and the green line, is equal to the angle in the opposite side of the triangle, split by the red line and inside the triangle. The second way to think about this theorem is that the angle BAC is the inside angle that is the opposite side to the angle at the tangent. Or the third way, which I prefer, is to take your pen and move it along 2 lines of the triangle and think about how the inside angle as being the alternative or opposite angle. So in our case here, for looking at the angle Y, we go up line 1 with the red line, and we go up to line 2, the yellow line, and the inside angle here is the angle, so there are the two angles that are both equal. And the same approach works for the angle X, where you can take your pen, move up the orange line 1, down the second line, which is the yellow line 2, and the angle ACB is equal to the outside angle here, AB. The third elimination step is to ask yourself if there are any lines that pass through the center of the circle. If so, you then have 3 theorems to consider. The first is the angles in a semicircle or half a circle, where the angle at the circumference is 90 degrees. The second theorem is the chord of a circle, where the green line or the chord is cut exactly in half or bisected by the red line from the center of the circle to the chord, and you therefore have 2 lines of equal length and a right angle at the point where the red and the green lines meet. And the third theorem is the angles at the center and circumference. In this theorem, the angle at the circumference is the angle at the center is twice the angle at the circumference. In this case, in this theorem, you have to think about having a 4-sided shape, 1, 2, 3, 4, but where 3 of the vertices A, B, D are touching the sides of the circle, and the 4th vertex is at the center of the circle. Try and get comfortable with moving the lines of the vertices A, B, and D along the circumference to change your visual perception of the shape. For example, if you were to make the red line and the brown line BD a straight line or a diameter, you'd effectively end up with the theorem above in the angles of a semicircle, where the center is 180 degrees and the angle A, or here, would be 90 degrees. The final elimination process is where you have 4 lines in the circle with 4 vertices touching the sides of the circle. And if you use your imagination, you could connect dashed lines to give you the impression of 2 triangles. This imaginary baseline is in fact the chord that creates the 2 segments of the circle, the major and the minor, or the other way around, minor and major. And that's why this theorem is called the angles in the same segment. If you remember, a segment is the space between the chord and an arc that it creates. And this dashed line or chord is not often drawn in maths books or questions, which can make the definition for this theorem even more confusing. In this theorem, the sides of the triangle AC and DB may or may not pass through the center of the circle. It doesn't really matter. The theorem basically says that the purple angles in the same segment, BAC and BDC, are equal. And if you moved your imaginary chord from the point BC to AD, and then you change your perspective of the major and minor segments, you will notice that the angles in the peach color, ABD and ACD, are also equal. In this theorem, try and get used to or comfortable by moving the vertices around the circle. Notice that although the shape of the triangle may change, the angles in the same segment remain the same. Now that we've covered the elimination process and the framework, let's see how we can go about answering question 21. There isn't much in this question that we can actually fill in apart from highlighting the angle ADC. So let's just go and mark this one out here. And by a process of elimination, we don't have any cyclic quadrilaterals in the circle, which means that we move on to step 2 in our elimination process, where we consider tangents. So we have a tangent of a circle here to the circle here, ADE. Let's mark that in there. And we're also given 3 choices of tangents. Tangents of a circle, which we just marked in. Tangents of a circle with externally connecting lines. We don't have a second tangent line coming in at all. And we also have the alternative segment theorem. Now, you could be forgiven for thinking that the alternative segment theorem has something to do with our question here. But if you look carefully, we don't have a 3-sided triangle, and this theorem also doesn't involve the center of the circle, so we can dismiss this particular theorem. Step 3 of our elimination process asks whether the shape has lines passing through the center of the circle, in which case you have 3 possible theorems. You will see that the third theorem, angles at the center and circumference, is the closest theorem for what we have in our question. And although it's not immediately obvious until you start moving the parts, point A around the circle. In this slide, I've drawn out dashed lines of A, moving us along the circumference of the circle and positioning A opposite O, so hopefully making a little bit more obvious that the theorem we're talking about is angles at the center and the circumference. So remember, when you answer these type of questions, always write down the circle theorem you're using. Now we know that the angle at the center is twice the angle at the point A, therefore we can write down, using this theorem, angles at the center and circumference of the theorem, that the angle BAD is equal to half of 64. So 64 degrees divided by 2 gives us 32 degrees. So this angle here is 32 degrees. Now we can then move the A back down to this point, still remains 32 degrees. Let's put that in there. And let's also label up this triangle and call it triangle 1 and give that a position of X. So triangle 1, calling it AXB. We know the total number of angles in a triangle is 180 degrees. So to work out this particular point here, we do 180 degrees minus 32 minus the 51 given here, and that gives us 97 degrees. You can write that in at this point. Let's just do this in a slightly different color. So you can see this point here is 97 degrees. Now, we still need to work out this angle here. We know that this is, I should put the right angle in there. We still need to work out this angle at this point, and we need to work out this angle here as well. Now, there's nothing else in our circle theorems that is going to help us work out what this angle is at this crossover. But if you do remember your geometry, there's the theorem called vertically opposite angles are equal. It's essentially showing that this type of image, the angles opposite one another are equal. So if we go back to our question here, we know that if this angle, we know that this angle is 97, therefore this inside angle must also be 97 degrees. So let's write that in as 97 degrees. So now we have, let's call this triangle 2. So triangle 2, which is OXD, which is again 180 degrees, is total number of angles. So to work out this particular angle, this point here, it will be 180 degrees minus the 64 minus the 97 degrees, which we got because we know it's opposite angles, and that gives us 19 degrees. So we now know from this that our angle, we can work out our angle, which we're trying to calculate, angle ADC, is equal to, if you remember, this is a 90 degree angle here because it's angled at a tangent. We've got 90 degrees minus the 19 degrees which exists here. And that gives us 71 degrees. So our answer for this question is angle ADC is equal to 71 degrees. So let's do a quick summary of how we solved this question. Step 1, we identified through our 4-step elimination process using the second step that we had a problem that involved using the tangent of a circle theorem. Step 3 in our elimination process allowed us to identify that the angle BAD fitted into the angles at the center of the circumference theorem. And that was critically done by repositioning the vertex A to help illustrate this theorem. The third step was actually identified using another rule in geometry where the vertically opposite angles are equal. And we found that this allowed us to find the angle in our second triangle. And the final step was recognizing that the angle we needed to find sat on a straight line and made an angle of 90 degrees at ODC, where we could calculate our answer. I hope that helped.